Hello and welcome to this Learn Oil Analysis video on acid, base numbers and oxidation degradation products such as varnish. Both acid and base numbers are important tests in determining the right time to change your oil to prevent acidic corrosion in your machinery. Acid numbers have a few synonyms including total acid number, TAN, TAN or AN, total acidity, acid value and neutralization number or neut number for short. Base numbers also have a few alternative names too, including total base number, TBN, BN, reserve alkalinity and alkalinity reserve of a lubricant. So why so many names to describe the same thing? Well, some are industry specific terms such as reserve alkalinity, which is often used in the marine industry. Others, such as neutralization number or neut number, are used by chemists to describe the way the titration test has been performed, including whether the end of the reaction, termed the endpoint, is measured by colour or voltage change. This video will give you a brief introduction to what the tests are, how they are performed and what the results mean. So let's begin. Let's start with acid number. No lubricant lasts forever, which, when you think about it, seems strange, considering many lubricants started their life millions of years ago. The problem is that the lubricants we use are very different from the base crude we extract, and the combined presence of heat and oxygen over time results in oxidation. Oxidized oils can form sludges in the machinery and also form corrosive acids that can attack metallic components. That is why we measure the acid number of a lubricant to assess how far this process has gone and time oil changes to get the maximum life of the lubricant, but to prevent abnormal wear formation. In engines, the problem of acid formation is compounded by the fact the fuel being burnt can form strong acids such as nitric acid from the nitrogen in the air, sulfuric acid, the same acid found in battery acid, acid drain cleaners and acid rain, is generated from the sulfur in the liquid fuel being burnt, or the hydrogen sulfide in sour methane gas fuels. Hydrochloric acid, the same acid in your stomach. It is generated from engines running on methane gases coming from landfill rubbish or trash sites with high chlorine. Where is the chlorine coming from? Well, usually domestic cleaning chemicals such as bleach that end up in landfill. Likewise, hydrofluoric acid, an acid used for etching glass, is formed from landfill methane gases with high fluorine, coming from all those used toothpaste tubes that are chucked away each day. With all these acids that can form in an engine, you may ask why your engine is not being eaten away constantly. The answer comes from a quite simple preventative measure that I use and perhaps you use at home. I'm going to let you in on a little secret. After I finish recording this video, I'm having a meal out tonight. Yum. In which I might eat a little too much and get indigestion. To avoid this, I'm going to take a couple of antacid tablets before the meal to reduce my risk of getting heartburn by neutralizing the acids in my stomach. This is the exact same way that lube oil manufacturers reduce damage from acids from combustion. They use the oil additive equivalent of an antacid tablet called a base number to neutralize those acids. Over time, the antacid will be used up as it is neutralizing the acids, and that is why in engine oils we also monitor the base number to time the best time to change the oil. If we take a look at the graph on screen, we start sampling a machine with a new oil change every month for a year without changing oil. In January and February, the base number is high, the acid number is low, and wear is also low. You may have noticed the acid number does not start off at 0, which, for the observant of you, may mean you ask the question, is the new oil acidic? The answer is no. It is just the additives react with the lab test chemicals in a similar way to acids, giving a false positive acid number. That is why it is important to have a baseline starting point for any acid number for trending purposes. You can find out more details on why new oils have an acid number in my blog article on learnoilanalysis.com titled Are New Lubricating Oils Acidic? As time goes on, you will notice as the acid number and base number come closer together and eventually cross, the iron wear rate increases. It is therefore a fine balance to time an oil change to get the maximum life whilst protecting the engine. There are a few ways to do this, including agreeing on an increase of AN above the baseline of a certain value, such as 1.5, or a base number decrease by a percentage, such as a 50% drop, or a threshold, such as a base number less than 2. Some people use the point of an AN and BN crossover as the point to change as well. Others look at a variation on the acid and base number and look at the overall pH of the lubricant when in the acid number test solution, called the initial pH, where the values of around 4 or 4.5 are common points to indicate an oil change. You can naturally change an oil earlier than these figures, but the issue then is the cost of lubricant consumption goes up. In fact, in some very large marine engines that use heavy or residual fuel oils that are very acidic and tar-like, they have separate lubrication for the cylinders. These lubricants can have 10 times higher TBNs than your average car engine oil, and they are single-use lubricants that run down the sides of the engine cylinders to neutralize acids. And the end lubricating oil, often called scavenge, cylinder or scrape down oils, are monitored to keep the TBN in the sweet spot, so it is just protecting the engine. Too little and there is wear, and too fast a feed rate and the expensive lubricant is being wasted. I just mentioned that some marine engine oils have very high TBNs at 30, 40 or even 70, whereas your average road vehicle may only be between 8 and 14. So why don't we make all oils have a BN of say 100 and you can keep your car oil in use for many years? You might think it's cost, but if I told you more expensive oils tend to have lower, not higher base numbers, this might seem strange to pay more for less. If we come back to my evening meal scenario, I could before my meal take double, even triple the dose of antacids so I don't have any chance of indigestion. But I don't, because I read on the side of the packet the side effects. The side effect of too high a base number than is needed is ash formation. So what is ash? Ash is formed when a small amount of the lubricant makes it past the cylinder rings to the piston crown. It burns like fuel does, but leaving behind the TBN metal additives, usually calcium or magnesium. These hot embers sit on the piston crown and can lead to pre-ignition problems, so that the combustion does not occur at top dead centre. Equally, the ash when blown out of the cylinder can block diesel particulate filters and coke up engines. So it is therefore a fine balance of having just enough of a base number that is needed to do the job. Hence you may have heard of low ash or low SAPS oils. So let's move on to how these tests are done. An acid number is measured in milligrams of KOH per gram. So that is how much alkali is needed to neutralize the acid. In colorimetric titrations, a colour change is used, similar to litmus paper, to test the change. In this case, the indicator is red-green, or arguably orange-green. We titrate a small amount of KOH to get the indicator, which is slightly acidic, to the neutral stage, so it has just turned green. We add a known weight of our acidic sample to the indicator and mix well. This changes the colour of the indicator back to red. We then add additional alkali until we bring it back to our green colour again. We now know how much alkali was needed to neutralise the known weight, so we have our acid number in milligrams of KOH per gram. Naturally, on darker oils we can't use colour, and so use voltage change called potentiometric titration. That's potentiometric. Now on to base numbers. To measure the base number, we just switch the solution at the top and titrate with acid, but we still use the units of milligrams of KOH, i.e. alkali, per gram, to allow for direct comparisons of measurements. So let's look a little more at the significance of acid and base numbers, their effect and their corrective actions. So if we take high acid number or low base number, the causes are usually overheating or overuse of a lubricant. For every increase by 10 degrees Celsius, you double the rate of reaction, and that means you also double the rate of oxidation, acid formation and base number depletion. This means you halve the life of the oil. Since this is an exponential process, an oil running 20 degrees Celsius above its ideal temperature, the oil will only last 1/4 the length of time, i.e. half and then half again. Other causes include changes in fuel quality, leading to high sulfur and high sulfuric acid formation. It may also be caused by addition of the wrong oil or leaking of the wrong oil into the compartment, which can change the acid and base numbers. The end result is thickening of oils, sludging, oil filter blocking and varnish formation. The solution would be, potentially, to change oil more frequently, check for evidence of overheating or test fuel quality. You can also have a too high a base number too, which is usually the wrong oil has been added, or in marine crosshead engines there is a leakage of cylinder oils into the sump. The result can be high ash, DPF, that's diesel particulate filter, blockage, and potential wasted cylinder oil. The corrective action would be to reduce the cylinder fill rate versus fuel usage and confirm the correct lubricants are being used. Another important effect of high acid number is varnish. In large hydraulic, compressors and turbine systems, a notable problem can be varnish, where the prolonged oxidation and high acid numbers can lead to the generation of sludges. These sludges can coat components in a varnish-like lacquer or layer, hence the name. Varnish generally dissolves well in high temperatures where it is formed, but as the temperature cools, it falls out of solution and precipitates on cold areas, usually areas such as cooling system parts designed to cool the machinery. This varnish then forms an insulating layer, preventing heat escape, generating more heat and more varnish, leading to more varnish deposition and forming more insulation. This vicious cycle continues until the system fails. But a popular way at the moment is Membrane Patch Colorimetry, or MPC for short. This involves storing a sample of oil in the dark to allow varnish particles to start to fall out of suspension and precipitate in the relatively cold temperatures outside the machinery and away from direct sunlight that can break down varnish particles. The oil is then filtered through a filter paper patch and the darkness is measured to determine the amount of varnish potential the oil has. The removal techniques include solvent removal by adding solvents to dissolve the varnish and then changing the oil, as well as filtration, which by Le Chatelier's principle, removing varnish, the saturated oil over the long term allows for varnish from components and system services to redissolve in the oil and then be removed by filtration again. This concludes the tutorial video and hopefully you're a lot more familiar with the importance of oxidation, acid numbers, base numbers and varnish in your machinery. If you enjoyed this video, visit our site at learnoilanalysis.com or subscribe to our YouTube channel. Thank you.